What is going on, guys? Welcome back to another video, and in this one we will try to build on what we did in the last video. So the last video was a paper walkthrough or paper explained of variational autoencoders, and so hopefully if you watched that video or if you watched some other video, you have an understanding of variational autoencoders and how they work and the derivation and so on. So this one we will build it, and luckily actually this is pretty easy to build. So the difficult part is understanding the theory and how it works. But now that we have that, I think this video will be pretty smooth. It will be pretty easy to build it, and so our goal is to build two functions here, one for the model, the variational autoencoder, and then set up a training loop to train it and do inference on simple data set, MNIST data set. But I think, understanding variational autoencoders is something that you definitely should do. I've been sort of like, I've known about, but this is really the time when I've taken it to really understand the details of it. And if you look at, variational autoencoders, they're used all over the place. Even if you looked at more modern approaches like diffusion models and so on, then variational autoencoders is a component of that. And I think understanding this thoroughly is a good investment. So with that said, let's get started. So, many people also when they code things, they have the code pre-written, and I've seen comments, people ask me to do that. For me, I feel like I like to watch someone build it, from scratch, explain it step by step, what they're doing, what's going on, and sort of be more chill with it in that way, instead of just throwing all the code and then go through it and it'll be rushed and so on. By going through it line by line, I can explain what I was thinking, and in many cases I have to sort of rethink myself and maybe pause and make a better explanation. But yeah, so that's, let me know what you think of having these types of videos, and if you think it's cool, if it's useful, if it's beneficial, then please like the video, subscribe, give a comment. All right, so for the model, we'll start with that. So we're gonna just import torch.nn. Actually, I think you should do this instead of doing import torch.nn as an n. It's a bad habit. I think you should just do from torch import nn. I think that makes more sense. But then, I don't know, this I usually do import nn.functional as f. Yeah. All right. And then maybe we should do like this. All right. So we'll do a class, variational autoencoder. We'll inherit from nn module. We'll do the init. Then we got to call this the parent method, right? So this is standard stuff. Then I'll write the skeleton code. So we're going to have an encode function. The encode function is what we talked about. It's going to be this is the Q of phi of Z given X, I guess. So, this is the encoder network. Then we'll have the decode, which will be where we send in Z, and we'll get back the image. So this is, if you follow that, I'll try to do, it's phi, no, it's P of theta of X given, God damn it, given Z. So we'll do a pass on that for now, and then we will have a forward method where we will sort of combine everything, or the encode and the decode, and that's it. So we'll then check. This is always a good thing if you build a model. Just build like do some random test case. So rand of 1,784 will do, and then we'll initialize the VAE. All right, but then we'll just print, I guess, the shape of it, but we don't have to do that now. Okay, so what do we want to do? All right, for the init, I guess, we need to know the input dimension, right? This is going to be for MNIST, that's 28 by 28, which is 784. So we'll just set input dim. We will have a hidden dimension. We can set that to default, maybe 200. And then the set dimension, we will set to default 20. So that's for the encoder, right? And also for, I guess, also for the decoder. So what we want to do first, right, for the encoder, this is when we take the image. So we will take the image and we will convert it to hidden dimension. So, and this is just a linear layer where we take the input dim to hdim. So in the encoder here, this will be first that we take it to a hidden dimension, and then so we have input image, we take it to a hidden dimension, hidden dim, and then we output mean and standard deviation. We parameterization trick, and then send it to the decoder, and then output image. Right? That's the idea that we're gonna try to do. So for this now, we will do hidden to mu, which is going to be hdim to zdim. And then we'll do the same hidden dimension to sigma. And that will be also, these are two separate linear layers. And remember, in the loss function is when where we specify that these, like what we want these layers to learn is that, well, depends. The loss functions are, there's two terms, but the KL divergence, right, will try to push this linear layer to learn a, or it will try to learn that this will be a standard Gaussian. Now, it won't become a standard Gaussian, but it will push it towards that because so that we ensure that the latent space is Gaussian. Oh, sorry. We ensure that the latent space is standard Gaussian, but we still have the reconstruction loss. All right. So we then have so this is for the encoder. Now for the decoder here, we're gonna have, this is right when we take when we have done the parameterization trick, so we've combined the mean and standard deviation. We will now take z to hidden first, so it's just going to be another linear layer, and then we will do hidden to image. So just the opposite straight up of what we did for the encoder, pretty much. Let's see, this should be this, and then input dimension. Cool. So now we got the initial. Let's now do the encoder. So this will just be image to hidden, right? We'll do image to hidden of x. Then we will do, so this will be h. We will do f.relu on this. Actually, I don't know why I did that. I kind of prefer to do, I think I like doing this more. And then .relu. Is this wrong? Oh, yeah, like that. So I don't know why I prefer to do it that way, but yeah, I guess both work. But I like doing this. So self.relu. Let me know which one you like. I haven't decided yet if I want to do this nn.relu or self.relu. Like doing using the functional, or I mean, it's a function, so it makes sense, but I don't know. It's like if you use the in place equals true here, then you just set it once instead of doing it all over the place, maybe. All right, but so hopefully, I mean, this would be pretty clear to follow. I hope I'm explaining things well. I'll try to see if I miss anything. But now we're just doing a right image to hidden, and then we do h. What we want to return here now is the mu and the sigma. So we're then gonna run h right? Mu sigma is going to be self dot hidden to mu of h, and then self dot hidden to sigma of h. Now I'm thinking, should this be relu on this? No, I don't think so. I think this should just be the linear layer. Yeah, that's good. Because I mean, if we put it to relu, it's going to be between 0 and 1, which I guess it's going to be in any anyways, but it can be negative values for the mu and I guess also for sigma. So we do not want to do relu here. And then let's see, we want for the decode, we take in z now. So we're going to take z to hidden dimension of z. This is going to be h, and then we're going to do self.relu on this. And let's see, after that, we're going to take the hidden to image. So I guess we can just return self.hidden to image of h. And that should be it. Yeah, actually one thing that's missing here is when we do the decode, when we output for this, we want to ensure that this is actually between 0 and 1, because that's what we normalize the images to be for MNIST. So here the pixel value should be between 0 and 1. So we use torch.sigmoid for that. So that's a decode. Now in the forward, we're just gonna put those two together. So we're just gonna first generate mu and sigma, which is self.encode of x. After we have that, we can do x re-parametrized, which is going to be mu plus sigma times, and then torch. This is epsilon, right? Maybe we can do that. Epsilon is torch.rand and like of sigma. So then, we element-wise multiply this, and this is, I think, default if you do it this way, by epsilon. So this will ensure that it's Gaussian. After that, we're gonna do x reconstructed is a decode, right? So we now run it through the decode with said reparametrized. There we go. And that's it. Reconstructed mu and sigma. So here you might be asking, well, why do we not just return reconstructed? Because mu and sigma is in the loss function for the KL divergence. So this is going to be for the reconstructed loss. This is going to be for the KL divergence. All right. I told you this was going to be pretty easy. I don't know. I'm trying to think if there's something that could be missing in the explanation, but this is, I think, pretty straightforward, especially if you watched the last video. All right, now that we have that, we generate just an example here. Maybe we can do batch size of 4. So we have 4 examples, each have 28 by 28, where we have flattened it. And we flattened it because we use linear layer here, right? And then we initialize this and the other default argument. So now we can try and run it. Model, and that doesn't work. God damn, always happens. Object has no attribute image to hidden. Image to hidden. I do have that image. Oh, image to hidden. Oh, right. We return. So we can do maybe. Let's see. VAE of x, we're gonna get back x, mu and sigma. Constructed, print x reconstructed dot shape, mu dot shape, print sigma dot shape. Maybe we can do that. So here we expect to get back the same in 2020. That's good. All right, so that means probably it's correct, hopefully. All right, so that's the model. We can remove that. Nice, makes it cleaner. Now let's go to the main or the train function. So again, I can just copy paste those actually. This I think is a waste of time to write. So yeah, all right, we're importing Torch, Torch Vision datasets as datasets. And by the way, if you're confused about any of this, if you're confused about building models in PyTorch and stuff, I have so many tutorials on PyTorch and the basics and building architectures and stuff like that that you can watch that is explaining the basics behind PyTorch. And so I'm assuming some prior knowledge of this, and it's hard. Like some of you probably think it's slow, and some think it might be difficult. So I'm doing my best. You can give me your feedback. But yeah, so Torch Vision datasets as datasets, where we're going to use that for getting the MNIST dataset. TQDM for a progress bar. Then we have NN for neural networks. From model, import variational autoencoder. And then one we just built. Transforms for image augmentation and stuff. Save image here because we want to see how it looks like. And then data loader for easier dataset management for batch sizes and stuff. All right, so we can start by doing a configuration. We're going to first set the device to be torch.device CUDA if torch.CUDA is available. Otherwise, we'll run it on the CPU. This should be run to, I think this should be fine to run on the CPU, probably, because this is pretty small. Then we have HDIM, which is 200, I think. Did we set 400? No, 200. And then 20. So these are just hyperparameters. I mean, this is, you can put, this is just going to constitute more compression. And this is just going to constitute more, let's see, this is just going to make it more, yeah, just more compute, I guess, more power to the network. I actually don't know exactly, did they say exactly how their architecture looked like? They probably did. I mostly followed on the theory of how they did it, not so much on the exact architecture that they used. I don't think it's that important, I'll be honest. But I mean, if they talked about it, maybe we could have done it. Yeah, I don't think they did. If I did, I must have missed it. But I don't believe they showed exactly how they did that. So I think this is probably fine. This is what I've seen other people use. Maybe you can play around with this if you want. I think maybe this, I mean, this is a little bit small, maybe, but it depends on the data set. I feel like for MNIST, this is, I think, plenty sufficient. All right, num epochs is 10. All right, batch size 32. Learning rate. I mean, all right, you should know what learning rate we use on this channel, all right? If you don't, get out of here. We always use 3e-4. Those of you who know, you know, and I shouldn't have to explain it. God damn it. All right, I'll explain it. It's the Karpathic constant. And you should always use the Karpathic constant. And actually, you should always also name, like when you use it, should always be the Karpathic constant, because I just feel like, I mean, the guy's done a lot, right? But he's never got anything really named after him. Like, where will Karpathy be? Like, you will like see his name. Like, there's no theorem like Karpathy's theorem, you know? Maybe if he would have become more of a theoretician instead of a engineer. But we should still honor him by keeping the Karpathic constant. Anyways, datasets.mnist root dataset. I've done this so many times. I'm just bored at this point. All right, so we're just loading MNIST dataset. We'll in this case we'll just do transforms.to tensor. All this will do is normalize it. So this will actually also divide by 255. So this ensures that the each pixel value is between 0 and 1, which is necessary that we if you come from like TensorFlow, for example, this is not clear that it does that, but it does divide by 255. So then the torch.sigmoid, which ensures that it's between 0 and 1, will actually work. And then we'll do download true. We'll create a training loader. So we'll do a data loader here. Data set is data set. Batch size is batch size. And then shuffle equals true. So yeah, here we're just using PyTorch to load MNIST, nothing particular here. We'll create the model, and we'll send in input dim, h dim, and z dim. And also we'll send this to the device we specified, which is either CUDA or CPU. The optimizer will be torch optim dot atom model dot parameters. Wait, oh, this should be device. Model parameters, learning rate is the learning rate. All right, so that's the optimizer. We're using, I guess we should do from torch import and then can you do optim as well? Yeah, so we'll do, instead of doing torch.optim, we'll do optim.atom. And then the loss function here, I told you could use, this is for the reconstruction loss function. What we'll use in this case is BCE loss. And we'll do a reduction sum. Now, like, I think you could also use actually like I don't know if it would work worse maybe, but you could probably do like a MSE loss probably, or like absolute error loss instead of BCE. The thing here is that usually with BCE, right, you have this, I think it's like this, you have yi, which is the label, times, if this is 1, you want the prediction to be 1, right? Let's Google it. BCE loss, PyTorch. All right, so for BCE here, you have this yn times log of xn, and then 1 minus yn times log of 1 minus xn. So here, basically, this is what you use for logistic regression, right? But then y is either a label of 0 and 1. In this case, the y will be pixel values of the input image. So these are the actual pixel values. So let's say that's 0.5, right? Then the target, so they say here, note that the target should be numbers between 0 and 1. And here they also say this is used for measuring the error of a reconstruction in, for example, an autoencoder. So if it's 0.5, then we'll be using both of these terms. And in that case, actually, the optimal will be to also have it as 0.5. So, yeah, this law still works. And yeah, I don't know. I think I was just a little bit confused about it because I thought it was only for binary labels and that you couldn't use floats, but it makes sense even for floats. All right, so here now we want to start a training, right? So we'll do, I guess this is not a good way to code it actually. It's okay for these like hacky types of things, but usually I like to do like a train function, and then like main run the train function and so on. But now I'm doing it in a sort of a single script because this is just sort of an example, right? It's a prototype, but I think for like multiple GPU or several if you're running on what is it called, for the data loader you have now I forget about it, the num workers, right? Num workers, yeah. If you do num workers and you don't do it like this, I don't think it's gonna work. But we're not looking for the most optimal code, I guess. Or so this is okay. We'll do a loop here. We'll use a TQDM enumerate of train loader, just so we get a progress bar. And then we'll do X and Y in loop. So remember here that actually we won't be using Y, I don't think. No, so yeah, you could just do underscore here because we're not going to use the label. So for the forward pass, we'll first want to get x to CUDA to device, redeclared x, define above without usage. Okay, I'm a little bit confused over that. But we'll do a view of -1 to input dimension. So we'll just keep, yeah, we don't have to do, we can do x dot shape of 0. So we'll keep the number of examples that we have, and then we'll just reshape it to input dimension. Yeah, I guess you could do -1 here, but it makes more sense, I guess, to reshape it. So view will reshape it to the exact, and I think like you could also use reshape here. I think view will do it on this one, sort of without making a copy. So I think it's a little bit more efficient, but sometimes you might need to do a reshape. So reshape could be a little bit of a safer option. All right, we'll do x reconstructed mu sigma. That's what we get back when we run the model. Now we need the loss function, or compute loss. So remember, we have reconstruction loss. So we have reconstruction loss. That will be our loss function of our x reconstructed and then x, right? So the labels here will be the input. And then we have the KL divergence. And this is the formula that we saw. I'll try to put it on the screen, but it's the formula we saw from the paper. It's 1 plus torch log of sigma dot power of 2. And then we have minus mu dot power of 2, and then minus sigma dot power of 2. So right, also important, since we want to minimize, right, we wanted to maximize in the paper, but we want to minimize here the loss by default with PyTorch. So we'll do a minus sign in front. And this is, I guess, already in that format. Yeah, it's already a minus sign here. So this will be, this is already good. So this will be the reconstruction loss and the KL divergence, just following the paper. This will push it towards standard Gaussian. This will push it towards actually being able to reconstruct the image. But now, after that, we want to do the backprop, right? So we'll do first compute the combined of the KL divergence. Now we're using a weighting of 1 for each. Maybe it's actually, like, I found that this worked, and they didn't say, but I guess, like, you in general, right, you would have some alpha term here and you could play around with the weighting of the two. But this seemed to work, like, just off the, like, just using 1. So I figured, let's not play around with it if it works. So we'll do, optimize 0 grad, loss it backwards, optimize 0 step. I feel like a lot of people do this, like, in some weird ordering. Like, they do, like, the optimizer. This is just me ranting, by the way, because I don't know, I'm bored, I guess. Here, like, they usually do, like, 0 grad over here, and then they do some loss backward, and then, like, they do some other stuff, and I don't know, like, I'm just confused. Like, it makes sense to me, like, just to optimize 0 grad. Now we know that there are no 0 gradient, like, there's no accumulated gradients from before. We'll do loss dot backwards, we'll compute a new gradient, and then we'll do this step. Like, I don't know, having it in this order makes things just make more sense for me. See? All right, this is good. Like, I just wanted to show you that this is a good idea. Look, he also does it, okay? Talking about, since we talked about the constant, I figured why not. So here you can see model 0 grad, right? Loss dot backward, and then optimize that step. Personally, yeah, okay. If you do the clipping of gradients, that's fine. But otherwise, it's in this ordering. Like, don't do anything else. God damn it. I'm venting. All right, so now that we have set up the training loop, I guess, like, what we could, yeah, so what I did here, I'm thinking of copy pasting this code because this is the important stuff. Like we can now run it. So hopefully it works. We'll see. So download. All right, this is a warning, user warning. That's from PyTorch. That's not from us, which is good. So all right, so it runs. The loss is pretty large, I guess. All right, maybe the learning rate is not the best. Yeah, it might be a little bit too large. You might want to decrease the learning rate just a tad bit. All right, so you know how we actually use this for inference. I'm gonna copy paste it because I don't know, the video is now 32 minutes long. Let's not make this longer than it has to be. I'll just explain this. So this is the important stuff. Actually, no, yeah. All right, so here what I do is for inference, I do model to CPU. Actually, let's rerun it and let's do just 3 epochs because it's gonna take a long time. All right, so we set it to the CPU. I'm not sure why I do that. I don't think you need to do that. But then we do an inference function, and what we send in here is the digit we want to specify, like the digit we want to generate, and the number of examples we want to generate for that digit. So for that, right, to be able to do inference, you need to have mu and sigma. For that, you need to know, you need to send in an image, get the mu and sigma, and then you can do the reparameterization trick many times, generate many samples, but you need to have the mu and sigma. So here I do images, and I run through index starting from 0. I run through the data set and I check if, if y is equal to index, then I add the image, right, to this list, and then I basically add index plus 1. And then we do that until we get all. So basically the first, it's a dumb way of doing it. I don't know why I did it this way, but so basically it will be like digit 0, digit 1, digit 2, digit 3. It's gonna be like that. So yeah, I guess until we have all the digits. This is pretty fast, so it's like no worry if it's inefficient. But then we have the encodings digit, and then we run through for each digit. Okay, so we actually do mu and sigma for each digit, all right? Then we actually generate, why did I do it like this? This is dumb. This is dumb. Oh, this is so bad. Can't believe I'm making a video showing this. So it's dumb because we're generating for all 10, but then here we're going through for the number of examples. Oh, okay. And never mind. It's not that dumb actually. I'm sorry for not following my own code. Yeah. So here we get all the images. We add them to a list. Here we get the mu and sigma for each digit. Here we generate a new image. We get the mu and sigma from that digit. We encode it, and then we run a loop where we generate. Sorry, I'm really tired. This is actually dumb. Yeah, it is dumb because we have the loop here, but we've already generated everything, but then we still run through. Yeah, so here you could do, if you want to do like, we could do that. We could, for many, you could do like 5 here and it will generate many like, yeah, we should do that. So what this will do is it will generate many digits of 0, and then it will do that for each digit because here we have the loop for each of the 10. So basically what we do is we run through the example, we generate epsilon, we do the reparameterization, we do the decode, and then we get it into a grid, and then we save the image. So what we get here, these are generated 0s and 1s and 2s. These look blurry, right? It's because it didn't run for that long, I think. This feels bad to do, but I'll change the learn. I think it's a little bit high maybe. I Actually, no. I will keep it and I will increase the batch size. You can always adapt. Remember that. And then we'll run it for 10 epochs. It's probably not as efficient, but I'll run it this way, and I'll get back to you with the results. All right. So 10 epochs. I still think so there are two things I'm thinking. The loss is not decreasing that much, and I think it should be. So it might be that either of one of these is sort of taking over, which you should probably check that, which one is taking over, and then also maybe decrease the learning rate a little bit. I would try, but it seems to work still. So here you can see these are with different parameterizations. One thing you can see though, like these are different zeros, right? So we've definitely succeeded with that. But one thing I'm wondering too is if you have like they still have like the same type of, like they're all tilted towards the same. For example, you could have a zero that tilts the other way, and there might be examples showing that in the training data. And if we would have saved that image here, gotten the mu and sigma from that one, maybe you could have directed it towards another sort of like the tilting of the digit or whatever could have been different. Maybe if we look at the one, you can see here also, like maybe here you could have imagined that the one could have been like more straight maybe, but I don't know. Just something that oh, these are bad actually. All right, some of them are a little bit bad, yeah. I think probably training longer and decreasing learning rate, I think that would have helped. Yeah, it didn't look that bad when I ran it the first time actually, so it might have been because of the batch size, because I ran 10 epochs but I ran with lower, so could have been that. But anyways, I think the inference thing is a little bit interesting. Probably, you know, I mean, yeah, I don't know. I still feel like the encoding, the mu and sigma, has a big impact on the inference step. And so it might, like, you can still get many different generations of sort of some of an original one, but it's still, it's not like GANs, for example, right? Like for VAEs, there's a term for it, but obviously for GANs, you can just send in a latent directly and then you'll you'll have it. But for VAEs, you need to send in the input and then be actually to be able to do inference and generate. All right, yeah, I don't think there's anything else. I'll upload the code, I'll put it in the description, or it will be on my GitHub. You can check it out there. Let me know what you think of the video. Hopefully it was educational and you learned about VAEs. Yeah, let me know what you think future videos could be on. I'm thinking right now I'm thinking of doing more paper reviews. I want to get more into the research right now and learn more about what's going on. Do some interesting projects maybe is a plan of mine. Yeah, I'm not sure if things aren't, like for this one, I felt it was so easy to hack a VAE and it's kind of basic. But for like larger projects, I'm not feeling like I want to implement like YOLO V7 like some monster. It's just, yeah, but I definitely want to start reading more and do more explanations and paper reviews. So let me know if you have any interesting papers that you think I should be making videos on and so on. All right, thanks for watching, guys. Leave a like, comment, subscribe, everything. Support the channel by doing that. And bye bye. Have a nice day. See you in the next video.